Without further ado, the next talk is about the Hydra Queue Runner, but in Rust. So let's welcome Simon and Janne.
Hi, nice having so many people here and interested in Hydra. So how many people are familiar with Hydra? Deeply familiar? 2 people. That's great. So let's look at the Hydra and what it currently does. The Hydra is basically our build system for Nixpkgs and some other smaller projects that are built currently, like PatchElf and GNU. It exists of a couple of components. Basically, the Postgres, which is a single source of truth, and it's the communication link between the components, and because we are using the Postgres queues and events. And then there's evaluator. Evaluator asks the Postgres for a job set, and then evaluates this job set, produces derivations, and writes builds into the database into the Postgres. Then there's the Queue Runner, the Queue Runner CPP. It monitors the database. It splits builds into steps, and then schedule these steps to remote builders, and uploads the build outputs into the store, also into any remote store, if there's a remote store configured. Then there are the builders, the remote machines, and the NixCPP version, the Queue Runner CPP version builds via the Nix protocol, and this is done via SSH. And last but not least, we also have the hydra-web UI, which you are most likely familiar with. It shows the current builds, the running builds, the latest build steps, and all of this. And it just basically queries the Postgres. It does not really talk to any of the other components. It basically always writes to the Postgres if it wants to do anything like bump a job to the front of the queue or cancel a job or anything like this. So there's also a diagram about this. There's the local store. The local store is the Nix store, obviously. The evaluator accesses the Postgres, gets the job set information, then evaluates the job sets in a bunch of builds, writes these derivations into the local store, and writes the results into the Postgres, or the build results. The Queue Runner monitors the Postgres queue, gets an event from Postgres, and then reads the builds table, and will then schedule these builds to remote builders. That's why also the Queue Runner has to run on the same host as the evaluator, because it has to access the derivations that were written from the evaluator. It reads those derivations and then schedules them. Afterwards, it can write to the remote store any outputs. The communication of the Queue Runner is done currently via SSH. So there's a subprocess, so the CPP application starts a bunch of subprocesses to the remote builders using SSH, and will use nixstore -serve-write, which is a really low-level interface, and you can basically use pipes to write Nix protocol into the remote store, and can use this interface to schedule builds and copy outputs and stuff like this. So the Queue Runner does directly the Nix protocol stuff into these pipes, and if you want to cancel a job, it basically only cancels the subprocess and the SSA connection. This is a bunch of bottlenecks. Besides, each build will need a separate SSH connection. We currently have the problem that we can no longer handle more machines. If you just went to the State of the Union presentation, the infra team, Jörg mentioned this, that we have more machines, but we cannot bring the builds to these machines any faster. This means we have currently further scheduling issues because everything is done in one queue. The queue is also not persistent, so every time the queue is reevaluated. We have also a lot of synchronous communication with the remote store. Oh no. It will hopefully not happen again. Synchronous communication with the remote store, and we are doing this while traversing the DFOs, which takes a lot of time. So Hexa mentioned this to me privately, that if we are currently merge staging into master, the Queue Runner has to go do like 20,000 head requests to the S3 store. It does this synchronously, and this takes a lot of time. And also, no one wants to touch the CPP code base. Most of the code currently written is exists there since 2015. So we decided to rewrite the Hydra Queue Runner in Rust 4 months ago. And who is we? Me, and also Janne. Janne is currently a maintainer of Hydra, so that's why he's here. We done this together with the Nixinfo team, mainly Hexa and Mick. And thanks to the foundation, Lazarus especially, who joined every meeting, and Frickler Handwerk, who helped with some organization. And thanks to the SDA, the Sovereign Technology Agency, which made this possible by providing some of the funds. So we started redesigning the Hydra Queue Runner. The goal for the redesign was that we wanted to support more builders, which was one of the most main goals for Hexa especially, and also for Lazarus. And we will have more builders, remote builders that need to be connected to them, so we can build more builds. Another performance issue, like I mentioned, is the faster creation of the steps, and especially the async integration into any remote store, S3, for example. Then we decided that we want a clean separation between queue runner and builder. Currently, because the Nix protocol is directly integrated into the queue runner, it's not cleanly separated. There's also extra logic for local building, for example, in the CPP version, which can just be resolved in the future with a local builder. I will come to that soon. And also better observability, debuggability, and improved maintenance, so that more people can contribute, easier bug fixes, maybe better scheduling algorithms can be explored in the future. What we built, so we re-implemented the full queue runner in Rust. We supported the current database scheme because the most communication is done through the Postgres and through the Postgres channels and queues and stuff like this. We can just hook into this and read from them, catch the same events, and write the same build information to this. We established a new builder communication protocol. We use gRPC for this. No particular reason other than this is a popular protocol that can be used for this. We are streaming NAS over this, so sending build inputs to the builders and accepting build results. And we added additional general messaging, basically, so we can check the remote usage, get health checks from the builders, that they are still working on the builds, and how is the current load of the builds. This new remote protocol gives us more flexibility. We basically can request the build. The queue runner can basically request a build and cancel a build. We are bidirectional channel. I will come to that soon. We get this heartbeats and the usage report purchase, which is mostly pressure, load, and stuff like this, and memory usage, which then can lead into better scheduling decisions. We use the gRPC protocol to stream the build logs at the same time as we're building them, and we stream NAS, which is mentioned twice. And also interesting is we no longer need any public IPs for the builders, because currently they're connecting through SSH with a public IP. We can, in theory, get rid of this because the builders are talking to the queue runner, not the other way around. So, and for this, the main idea is that there is a bidirectional channel. The builder basically says, hey, I want to talk to you, I want to build something. This can be any machine. It just can connect to the queue runner and sends a join message, sends the host name, stuff like this, so we can identify you. There's also authentication, but we'll talk about this later. And it sends a join message, the queue runner acknowledges this, and afterwards we send a ping message basically every 10 seconds, which is the current load, and stuff like this I'll mention. This gives us the scheduling and monitoring benefits I talked about, CPU, memory, disk pressure, stuff like this. So for example, we are currently running the queue runner already in production at Helsinki Systems, and we sometimes have an issue that we have a full disk. So we can take this into consideration, stop scheduling builds to the runner. Go rebalance load across across the builders. The internal design of the queue runner is that there are basically 3 tasks. There's the queue monitor task, which watches for any new events. So, for example, there are new builds, or builds are bumped to the front, and stuff like this. This is every time we get an event from the Postgres database, we need to take a look. These events are sent by the evaluator and the Hydra UI. And once this happens, we will reevaluate the open builds. And then there's the dispatch task. The dispatch task is this will then dispatch those builds to basically the builders. And then there's the uploader task. The uploader basically will then write it to the remote store. So we are doing this on a separate thread. And so you can limit uploads the concurrent uploads at the same time. This ensures that only one task can insert new builds into the basically internal state. And we are also this also ensures that only one task can schedule a build, because we need to ensure that the same duration is not scheduled to two machines at the same time, unless, for example, there's a build failure or the build got cancelled. Then we are allowed to reschedule it. We then also have event-based, so everything else like the gRPC communication, like streaming the logs, is event-based, and the HTTP request, there are a couple of endpoints, additional endpoints to get information about the internal state of the queue runner. This is done via event-based. Yeah. And the queue runner keeps the current builds in process. It does not write anything to the database, and about the internal state, it only writes build results to the database. Yeah, and so we keep the complete dependency tree of the builds we are currently working on in memory. Then the build pipeline. The queue runner is responsible for processing these new builds. Like I said, it's triggered by a Postgres event. It then gets all open builds and the durations. It traverses the duration tree manually, so we are checking, hey, is this duration already done? So basically, we already have the outputs. Or is this a cache failure, for example, if we already know that this duration doesn't build, this is stored in the database, so we can check this, and then basically skip everything down in the dependency tree. We changed the traverse of this to an asynchronous traverse, which required a lot of mutexes and rewrite logs, but it generally improves the performance because we have to check the store a couple of times. We also have to talk to remote store, which are a lot of head requests to the CPP version currently sends. And we also still need to do some Postgres operations. All of this can be done asynchronously, and it generally improves the speed of new builds being scheduled. Once a step exists and is runnable, then it is inserted in a build queue. What are runnables? Let's look at this graph. So we have at the top level we have the build. The build is a DFO generated by a job set, and down there we have the dependency tree, for example. All these leaf nodes are runnable. So basically, dep is a runnable because we no longer have any further dependencies to this. To this dependency or to this duration in this case. And this is basically constructed in the internal state. And once a job is runnable, or once a step is runnable, it can then be scheduled to any job. And if you, for example, schedule these two builds at the same time to 2 different machines, the next state would be that these two dependencies will then be runnable, and we can go do this further. So, for example, next time we schedule these two builds, and these are now done, meaning this and this is now runnable. This should not be runnable yet, but yeah. All of this get runnable, and these jobs get then scheduled to builders. In the end, everything is built, and we have an empty build queue. So we did some more changes. Currently, there is only one build, one queue per platform. So we have one queue prepared. This is sorted, and for all platforms. So basically, there's x68 and Darwin in the same build queue, which caused some problems. That Darwin builds are prioritized above x68 Linux, for example, and yeah. We isolated the build platforms into multiple queues, and these queues are now also sorted in a similar way, based on the priorities. For example, if you want to building a job, it gets a new priority. The priority will then be the local time, the current time, and the scheduling shares of the job set. This makes it generally that we have a better scheduling per platform and smaller runnable queues. And next part is dispatching tasks to that get triggered, and the next part is the dispatch task, which triggers runnables to machines. If a runnable is already scheduled, we ensure that it's not scheduled again. We then create a build step in the Postgres database. So if you ever open the build in Hydra UI, you see that there are a bunch of build steps. These are the dependencies that need to be built. The queue runner then finds a free builder. It determines this by a couple of metrics, like for example, you can say, hey, this builder can have a max job count, which is the scheduling that the old queue runner uses, or you can do some dynamic scheduling based on pressure or load. Load if you are on Darwin. Then the runnable gets linked to the builder, so we are storing the information if the builders, which builder will switch runnable. And the basic message is that we are sending the build message into the channel, also the bidirectional channel is the only way the queue runner can talk to the builder. It sends basically a build message, which this derivation with this build options, for example, the build timeout and silence timeout. Afterwards, the builder it's a separate binary, and it acts independently. It fetches the NARs and imports those into the local store from the queue runner, but only missing NARs. So if you have a local host builder, it does nothing in this part. Then it starts the build and it processes, and at the same time streams the build outputs logs through the gRPC protocol to the queue runner, so the queue runner can store it on disk, and you can see the logs while it builds in the Hydra UI. And once it's done, we are uploading our build results and sending information about the build. So this part can also be done at an earlier stage. For example, if the build fails or if an import fails, we are sending information about it to the queue runner that, hey, the build fails or some dependency failed or something like this, or the import failed. Depending on the build failure, there's also some logic about rescheduling, which can be configured. So you can builds are rescheduled if the import failed, but if the build itself failed, then there's no rescheduling. Some results. So the new queue runner is deployed for 8 weeks already at Helsinki Systems. We sadly don't have any remote store. We only have the stores itself, which are served via Harmonia. But this part, the remote store, was then tested in the Hydra staging. The official infra team has been staging Hydra for a couple of weeks now, and it also has the new queue runner deployed. We tested it with an S3 remote store, which is located in NA, I think, and we traversed 6,500 steps in less than 60 seconds. There's a cutoff time for the queue check. Otherwise, we cannot react to any changes in the queue. So the queue check gets cancelled after 60 seconds. So this is really important that we get this time low. Also, the queue runner is merged into the Nix community Hydra like 3 days ago, which is quite exciting. They are using this in production to build Emacs overlays or something like this. And we have implemented, we are basically feature complete. This is not a half rewrite. We have all features that the old queue runner has re-implemented in Rust. The migration path is also really easy, so we are trying to get this merged in production Hydra. There are currently the infra team is still testing, but migration path is pretty easy because it's compliant with the database. We don't have any database migrations yet. We are planning to clean up the database a little bit, like 32-bit timestamps. So the queue runner can be swapped back and forth. Because we implemented the same protocol via the database. We also had one outage, like I forgot to disable auto update, and we went back to the old queue runner for a couple of days. Some downsides that the new implementation has is that there is some protocol evaluation. This requires versioning. So if the queue runner itself chases the protocol, then all the builders need to be updated at the same time. Otherwise, they can't speak the same protocol again. And protobuf messages can be lost. So this requires, in the future, backwards compatibility fields and versioning, stuff like this that works easier. Also, the new queue runner has this second binary, the builder client, which increases deployment for the info team and stuff like this, but this was evaluated. And we have a more complex authentication. Previously, we only had to share SSH keys. Now we decided to use MTLS, which requires a CA chain. A little bit more overhead, especially for people who run the Hydra Queue Runner locally or something. Conclusion. We did rewrite the queue runner completely and solved the SSH scalability issues. We gained performance, observability, because we use tracing, forgot to mention that. And we have a more extensible protocol where we can share arbitrary messages. We also have smarter scheduling, because we can take the current load and pressure into consideration. And yeah, this should result into more concurrent builders. Still needs a little bit more evaluation, but yeah. And we presented a smooth migration path. Outlook, we are currently working on more, also there can be more advanced scheduling policies, for example, like costs can be quite difficult to compute, for example, when a host is actually busy, or for example, you can deploy 20, 30 Python jobs to the same machine, but you can only deploy one Chromium build, for example. And we also plan on doing some work for CA derivation, getting CA derivations into Hydra in a more usable way. Thanks for your time. Any questions? No.
We're doing a lot of crazy evals because we have Haskell builds, so they become quite big and they have a lot of IFDs in them. And sometimes what happens is that because both Hydra and the IFD builds that are happening in order to eval in the evaluator, both you use the same Nix distributed builds protocol, right? Which is basically not a protocol. Sometimes the evaluator blocks out the queue runner from scheduling new builds. Is there a way maybe with the new queue runner to hook the evaluator IFD builds into the queue runner so that at least you see when the queue runner is being blocked by that? So for example, we have an alert when Hydra appears to not be building, the queue is full, but there's nothing happening. We get woken up for that. Maybe there's a way to make the IFD builds visible in the queue runner as well.
Currently not, but maybe this can be talked about.
Can I? Okay. Currently no, because the Hydra isn't really evaluating itself anymore. This got moved out into Nix eval jobs, so it's a third-party project now. So if they implement a feature like that, then this would be possible, like some hooking feature, but you have to talk about that with MiG92, I think. Yeah.
I just want to say thank you for this, because the amount that Nixpkgs is held back just by not being able to make use of compute resources is so intense. As from the Nixpkgs CI team, your ability to say yes, this thing's cutting out. The ability to say yes to like the large changes is so powerful, and this will undoubtedly unblock it. Thank you so much.
Is this microphone? It is working. What happened? Okay, we have. I don't know how many questions we have. I can't really see the AV team. Whatever. Okay, you're next.
So you've been using this new scheduler in your company for 8 weeks.
Yes.
Did you also collect metrics, like, for example, how much performance improvement or did the reliability increase? I'm very curious about that.
Yeah, I plan to collect metrics, but I never actually came around to it. The new Queue Runner, we have some adjusted Hydras and adjusted UI in the Hydra, which shows the more advanced UI for the machines. And we are collecting more metrics, so the new Queue Runner has a better metrics collector and exposes those metrics through also Prometheus metrics, but we never actually came around to actually collecting them for more weeks, which is a oversight.
Thanks very much. We have a lot of trouble with Hydra's Queue Runner. This will solve a lot of issues. You mentioned that you are now using a gRPC protocol to the builders, which is a great improvement.
Yeah.
Does the remote builder only talk to gRPC to the Hydra Queue Runner? So it's effectively rewrapping the Nix daemon protocol in gRPC. Is that
not exactly the daemon protocol, but we are basically we are basically saying, hey, I want, for example, to get this NAR, and the NAR is then streamed via gRPC, and we are then talking through the Nix, not CLI, but FFI interface. So to say, like, I want to import this binary.
Do you think there's any possibility that the gRPC version of the Nix protocol would be extractable as a thing?
There are currently some talks about this, but nothing.
Thanks.
More questions? Okay, over there.
Is it possible in future with this architecture to pit builders against each other? Because you mentioned that currently only one builder can get one task at a time.
Yeah.
Could it be easily extended to pit multiple against each other? Like to have like same task fan out to multiple builders and see which finishes first.
Technically, yes. You have to get around the fact that we currently have to ensure that their files are not scheduled multiple times. So it would need some changes, but possible,
Okay. I'm being told I need to cut this off. I think we have the lunch break now, right? Yeah? All right, so let's thank our speakers again.